Okay, we can begin. So, welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are very happy to have Sabir Ramazanov from MSU Moscow as this week's speaker, and he is going to tell us about domain walls and their gravitational waves. So, let us begin. I'll send you a reminder when 5 minutes are left.
Okay, sure. Okay, so first of all, I would like to thank everyone. Thank for inviting to give this talk, in particular Nish. And I will talk about my last two free papers written in collaboration with Evgeny Babichev, Ivan Dankovsky, Dmitry Gorbanov from Samantha, and Alex Wickman. Some of you may know Rome Samantha, and but I emphasize the role of this guy Ivan Dankovsky, who is the master student here at MSU and who is already quite good at running lattice simulations. So the work which I'm gonna talk about became possible mainly due to him. Uh, so. Um, of course, the main motivation for this activity is the recent discoveries of gravitational waves, and mainly the discovery, or more, maybe it's more careful to say, a strong indication of existence of a stochastic gravitational wave background by nanograph, APTA plus India PTA, Chinese PTA, and PPTA. And this has been possible due to this discovery largely is due to pulsars. Pulsars uh, some sort of very precise clocks in our universe, and studying the arrival of pulses from these pulsars is a very advanced measurement, and even a small disturbance, for example, due to gravitational waves, can affect this pulse timing arrival. And this is the basic idea how this how this measurement has been made possible. Uh, so. Uh, uh, the characteristics of a stochastic gravitational wave background are still with some quite big uncertainties, but it's the amplitude of this background gravitational wave background measured in terms of this fractional energy density, which is the spectral energy density of gravitational waves per total energy density of the universe. And the main characteristics throughout my talk, which I will mention quite often, will be the spectral index of this gravitational wave background, which is about the spectral index is 1.8 plus minus 0.6. Okay, nanograph is and PTAs are usually using some different notions, so this is um, uh, with these conventions, it's 1.8 plus minus 0.6. So the main candidate for the stochastic gravitational wave background found the most widely discussed is, of course, from supermassive black hole binaries. The primary reason I would mention is that compared to many other sources, we at least know that supermassive black holes exist. So there have been Nobel Prizes for that. But one should mention that the story is not so simple. And for example, gravitational wave driven supermassive black hole binaries predict the spectral index, which is somewhat different. It's two-thirds, which is different from 1.8 plus minus 0.6 measured by nanograph. There are also other problems like final parsec problems. So for supermassive black hole binaries to emit gravitational waves efficiently, they should be already quite close to each other, and it's not so easy to bring them sufficiently close to each other. So this is the so-called final parsec problem. And there is, of course, the It's known that supermassive black holes are notoriously difficult to produce. So for this reason, it's absolutely makes sense, in my opinion, to consider some other more like sources from early universe, and nanograph collaboration itself performed some analysis. They had the paper and with cosmological interpretations, scaling induced gravitational waves, first order phase transitions, cosmic strings, and domain walls. Domain walls are usually not so popular in cosmology, and um, with this paper nanograph kind of with this but the situation may have changed, may probably will start to change with this discovery of stochastic gravitational wave background. Okay. Can you hear me, by the way? It's all fine, right?
Yes, sir, it is fine. Thanks.
Okay, thanks. So as it follows, I will focus on the case of domain walls. First, let me describe what are domain walls. Domain walls are some topological defects which arise in some models with spontaneous symmetry breaking, with spontaneous breaking of discrete symmetries, and I will focus on the simplest case of Z2 symmetry. So I will consider most of my talk. I will deal with this. If I will refer to some Lagrangian, then it will be simple Lagrangian like that. So this is the scalar field chi constituting domain wall. It's Z2 symmetric, and the Z2 symmetry is spontaneously broken by the expectation value V. So it is known that in 1+1 dimension, this Lagrangian, this field chi has the following static solution known as kink, which describes interpolation of from one vacuum, say minus V at minus infinity, to at minus partial infinity, to plus V at positive partial infinity at plus Z. Okay, so it's a kink. It's known as a kink solution, but and it's in 1+1 dimension, and we know that, and we are living in a 1+3 dimension, and so domain wall is just an embedding of this kink into 1+3 dimensions. So what is pictured here is with bolt. It's a domain wall. One should understand that there is a section of this domain wall. So if you will zoom in the domain wall and will look into its structure, it will be a kink here. Domain wall is a two-dimensional object with a cross-section described by a kink. Okay, and domain walls are splitting the universe into regions with positive and negative vacuum, so they create a non-trivial topological structure in our universe. Okay, so what is pictured here is sufficiently thin domain wall, and it's a good idea to visualize domain wall like that. It's sufficiently thin, so the wall thickness, which is basically inversely proportional to the mass of the field chi, of the particles chi. It's usually sufficiently small compared to the another characteristic scale, which is the Hubble radius. So that's why one usually refers to the so-called thin wall approximation. Well, in the simulations I will be talking about, it has never been used. It's just for convenience of visualization of domain wall. Okay, and there is domain wall tension, which will be also quite important, and it's just the energy density of a domain wall and integrated over the domain wall width. So, and this is just proportional to the expectation value to the power 3, which is obvious also from dimensional considerations. Okay. In my talk, normal people usually consider the expectation value to be constant. So this is like the case of a Higgs field. And in the part of my talk, I will also consider the case of constant expectation value, meaning that the domain wall width is constant and the tension is constant. So I will sometimes call these guys constant tension domain walls, and these are the most standard objects considered in the literature. But in the final part of my talk, I will also talk about the so-called melting domain walls, in which case the expectation value is proportional to the universe temperature, which is also a possible situation. And in that case, so the expectation value drops inversely proportional to the scale factor, and the tension is decreasing, and at the same time, the domain wall width is growing. So these have been the goals of my last papers with colleagues, is to study evolution, numerical evolution, and also theoretically of both standard domain walls and melting domain walls, and their gravitational waves study the evolution at radiation domination, which is the most important thing from the viewpoint of PTAs. And we did this analysis using the publicly available cosmological code developed by Figueroa, Florio, Torrenti, and Valkenburg. And we used these lattices, different resolutions characterized by grid numbers, different grid numbers, 512, 1024, and at maximum 2048. And the relevance of the fact that Cosmolatis is a simple and publicly available code is that in principle everyone can use it. And in our papers we described, and in my talk I will mention some obstacles which you can meet when running Cosmolatis, and some ideas on how one can avoid these obstacles, and in principle how can one usually reproduce the results of numerical simulations for domain walls, like sitting at home and probably having an access to some not very well, not the most developed even cluster. So I will start with constant tension domain walls given by constant expectation value. Many results are just very similar between constant and melting domain walls, but there will be crucial differences. So once again, I start with I will talk about standard domain walls, and I will mention when I will switch to melting domain walls. So these are how the domain wall looks in the lattice box on a lattice. In the simulation box, it starts with a very complicated configuration. Some bush, and that's with some time some gardener came and cut some bush, and they took a much more elegant form at later times. So the idea is that the picture of domain wall, the snapshots of domain wall evolution are getting dramatically simplified with time. So, and one can also observe, I will make it more clear with time, that there is actually just one domain wall, and it's surrounded by small domain walls, which are not so relevant. So, but essentially there is one long domain wall stretching throughout the simulation box. And this simplification of the domain wall evolution, that domain wall structure, the network, domain wall network is getting simpler with time, is a manifestation of the scaling law. So the scaling solution is the attractor solution, which is typically reached by the domain wall network with time. Okay, so in more strictly speaking, the scaling solution is a self-similar solution characterized just by one length scale, which is just the Hubble radius, and that's it. So, and as one consequence of this scaling solution is that there is just a fixed number of domain walls in the horizon volume at any time. So with time, horizon radius is growing, but if you will look at the qualitative picture of what is going on in the horizon volume, it just will be always the same. It will be always the same number of domain walls in the Hubble volume. Specifically, there will be, in fact, just one sufficiently small domain wall in the Hubble volume. And this is the most mm, characteristic manifestation of the scaling regime. So, this has some consequences. Actually, okay, this is all qualitative, but one can check the scaling regime quantitatively using this parameter called the scaling parameter. So, it's basically the area times time divided by the scale factor and the volume which is captured in this domain wall area. And the manifestation of a scaling regime is that this size should get constant with time, and this has been proved also before us many times that this parameter size, scaling parameter, becomes constant with time, meaning that one has reached scaling. Here we have this should be this happens literally independently of initial conditions. So whatever initial conditions you throw, this parameter psi will enter the constant regime at some point. But there are some, not everything is so immediately clear at the moment. So there is some small discrepancies depending on the type of initial conditions. So while all initial conditions lead to constant psi at late times, there are some small discrepancies. For example, for vacuum initial conditions, this parameter psi is slightly larger, so it's about 0.8. While for thermal initial conditions, this psi is slightly lower, it's about 0.6. We don't know the physical origin of this, and it will not be so relevant for my talk, but it's something to think in the future. As I said, that there is only one domain wall in the horizon volume. So one can estimate this energy density of domain walls as the tension of domain walls times the area of domain wall in the horizon volume, which is just the Hubble radius to the power 2 divided by the Hubble radius to the power 3. And then one will get the simple the simple expression for the energy density of domain walls in the scaling regime, which is surprisingly accurate within a factor 1 or 2. So another interesting thing about the scaling regime, which is not so crucial for my talk, but that the scaling regime usually starts not immediately. It starts with some time, and there is very characteristic time when it starts. It's about when the domain wall width becomes about 5% of the horizon radius. And this is a very universal rule, and we practically did not see violations of this rule, independently of initial conditions, also for melting strings, as I will talk more about it. Okay, this behavior of the energy density of domain walls, that it's just proportional to the Hubble rate, and sigma wall is constant. Recall that we are still working with standard domain walls, is actually quite dangerous. As one knows, probably there is the so-called domain wall problem. Meaning that the energy density of domain walls drops very slow at radiation domination, okay, not only at radiation domination, versus the radiation energy density, which drops as T to the power 4. And here it's T to the power 2, because the Hubble is proportional to T to the power 2, temperature of the universe to the power 2. And it means that the energy density of domain walls is growing relative to the energy density of radiation. And generically, one would expect that domain walls will overclose the universe, and so basically domain walls are too energetic, and the problem for standard cosmological evolution. Of course, there is a way to solve the problem. One can always assume that this domain wall tension is very small, so we can, if you will make it smaller than MAV to the power 3, which is the Zeldovich bound, then you can avoid the problem. But it's just not interesting phenomenologically at all. Another solution of the problem is that one explicitly breaks the two symmetry, so one adds some bias terms. Okay. One adds some bias terms, and in that case, one can adjust this breaking of the two symmetry in such a way that you destroy. So with this symmetry breaking term, you create the bias between asymmetry between different factors. And at some point, some sort of first order phase transition happens, and the whole system falls into the true minimum, and the whole network of domain walls gets destroyed. And okay, it can happen that the Z2 symmetry is explicitly broken. In practice, people nowadays, these days, are starting to implement these Z2 symmetry breaking terms into simulations. We did not do that. In our case, so when you run the simulations, you are running it for a finite period of time, and this period of time for us has been always relatively small, such that domain walls never came to dominate evolution of the universe. But for consistency, one should take into account this term, and the proper simulations of domain walls in principle should take this into account. And I will tell a bit more about this. But for the time being, just please ignore it. Before I will go on with gravitational waves, I would like to mention one very important thing about domain wall. So about the scaling regime. So scaling regime is when there is one domain wall with horizon wall volume, sufficiently smooth domain wall. And, uh, and reaching the scaling regime actually requires that there is a mechanism of energy loss. So the main wall should emit particles sufficiently efficiently enough so that the scaling regime would take place. And these particles are usually expected to happen from the collapse of closed walls. But in fact, as I said, there is what we see is only essentially one long domain wall stretching throughout the box. Okay, there are some small closed walls, but the total area of all closed walls relative to the long wall is very small. We don't think that the closed domain walls in this picture play any role. So this is raising the question how the scaling mechanism is working. In this regard, I would like to mention, so we are tending to agree that with the early work by Gragunis and Heidmarsh from more than 20 years ago, which came to similar conclusions, and they concluded that the energy loss mechanism appears to be direct radiation from a long wall. And this is very different from what one has in the case of cosmic strings, for example, where one efficiently produces loops of cosmic strings, and they're responsible for entering the scaling regime. Here, the story is very different. Okay. Let me switch now to domain walls, to gravitational waves from domain walls. Okay, domain walls are just made to emit gravitational waves. The reason is as follows. By construction, topological defects are spatially homogeneous objects because they are describing how the field in some places of space is transiting from one vacuum to another. Apparently, it's inhomogeneous structure. And then it's known that the gravitational waves or transverse traceless fluctuations of the metric are solved by the spatial inhomogeneities. So, as I said, domain walls are very energetic. This is a problem, of course, but on the other hand, it's how to say, blessing, because most energetic gravitational waves are emitted when the domain wall, when the source is large. So larger is the source of gravitational waves, more gravitational waves we can expect from that. And most energetic gravitational waves are emitted when the domain wall network is just about to be destroyed. So, without going into details, let me mention that while the gravitational waves are being sourced by the scaling network of domain walls, the energy density of gravitational waves is almost constant. It's related to it's fed by the tension of domain wall squared. And since it's constant, once again, while being sourced by domain walls, after the domain walls will be destroyed, gravitational waves will decay in the standard fashion, just like radiation. But while they've been constant, the energy density is growing relative to the energy density of radiation. So once again, the biggest signal is expected at later times. So more we yeah, more domain walls evolve, more they emit gravitational. Yeah, I mean, the signal of domain walls strongly depends on the moment when they're being destroyed. So as I said, okay, well, the characteristic scale, due to scaling, scaling suggests that the system is described by the only the only relevant length is the Hubble radius, and so the characteristic frequency is expected to be about the Hubble rate. And if one and this is very good for all gravitational wave experiments, because if you will rescale the Hubble rate to present, and if you will take the characteristic emission times of domain wall network from 100 MeV till 10 to the power 10 GeV, one which are most interested from the viewpoint of radiation dominated stage. Then one covers all the interesting experiments from PTAs and Dyson telescope. Once we're interested in the PTAs at the moment, okay, not necessarily that, then the domain wall network should be destroyed at temperatures about 100 MeV. So let me show the results of simulations. Most of them, I would say, it's exactly the case. It's the case where expectations just meet reality. So there is a peak of gravitational waves which exactly corresponds to the Hubble rate. Okay, not exactly, but with the difference is factor like 0.7. It's not something relevant. And since with time the Hubble rate is decreasing and the maximum is shifting to the left. So this change of the maximum with the simulation time is just a reflection of the flow of the Hubble rate. Okay, also the kind of trivial part of the spectrum is its infrared behavior. It's clear that it's the slope of the spectrum, which is approximately power law, is very close to 3. Okay. And this is called a causal tail. So ideally, it should be 3 in the deep infrared. If you would be able to go infinitely to very small frequencies, it's about 3, and it's just a causality tail. So mm, it's kind of this 3 is like, I will not go into theoretical details, and it's one of the most commonly observed spectra, gravitational wave spectra in the literature, along with the flat spectrum form inflation. And so once again, this k to the power 3 in the infrared is due to is fixed by causality reasons. And yeah, and the life hack is if you asked what is the spectrum of gravitational waves and you don't know, quite often it's k to the power 3 or just flat spectrum. Okay, but the ultraviolet part of the spectrum, okay. So here I would like to remind that it's we are not the first to run the simulations of domain walls to obtain gravitational wave spectra. So there have been probably, I would mention, these three groups. So I don't know more, but maybe if you know, please let me know. We are there is almost perfect agreement, as I said, in the infrared part of the spectrum, and which is also most described by just theoretical, most fixed by just theoretical arguments. But yeah, we are discrepant in the ultraviolet part. So what we see in the ultraviolet part is somewhat different, and in my opinion, it's something where the most interesting physics may appear. So first of all, the near the peak, the slope of the spectrum. There are simulations which say that it's just -1. But many later simulations, including ours, are rather indicating that the decline of a spectrum is sharper. So it's rather something like -1.5 and even steeper. Okay, somewhat depends on the running time of simulations, even in the scale, or even when you have already reached scaling regime. It's somewhat dependent on initial conditions, unfortunately, but we always see the steeper spectrum compared to the naive n equals -1, which has been obtained in the early simulations. But okay. The other thing which is for which I don't know the physical justification is that okay, there is a power law drop-off, but there is the power excess at some intermediate scales. Okay, so the spectrum somehow at intermediate scales exhibits some flattening, which is particularly clear on the right spectrum, which is obtained with thermal initial conditions. So here we use just two types of initial conditions. And okay, and on the very right there is steep cutoff, which is due to a finite wall width. Where finite wall width at very large K comes into play. It plays the role of the ultraviolet cutoff for gravitational wave spectrum. So I would like to mention how this could be useful in the future. So if this plateau-like behavior persists with later simulations, which is should be checked properly, in my opinion, then in principle it can happen that if Lisa sees something plateau-like, maybe one should not make immediate conclusions that it's cosmic strings or something like that, but it could be in fact domain walls due to this unexpected feature at intermediate scales if it fits into the Lisa frequency range. Okay. So, okay, and just a couple of details, just for those who would like to study in more details domain walls. It's like when you just start running domain walls, the simulations of domain walls, and in particular the spectra of gravitational waves. What you see is not immediately this sufficiently smooth spectra. What you see is something different and something bad usually. So besides the peak at the Hubble rate, which is due to scaling reasons, there is some other peak in the ultraviolet, and which can be proven to be of non-physical origin. The proof which we use, in order to prove this, we use the cross correlation of lattices with different grid numbers, 1024 and 2048. And this ultraviolet peak clearly was moving as we changed the resolution of the lattice, which clearly proved its non-physical origin. But the most non-trivial part was to get rid of this ultraviolet peak, and at the same time to do not get rid of everything. So to leave, to understand what is physical and what we can trust, and what is non-physical and we cannot trust, and to reconstruct the full spectrum. So once again, we use cross correlation of lattices at different resolutions, but besides that, we used another non-trivial thing is that we were obtaining the gravitational spectrum by parts. So first we focused on the central part of the spectrum, and we did not care about how bad it goes in the infrared and ultraviolet. Then we focused properly on the ultraviolet part of the spectrum, then on the infrared part of the spectrum. So we separately obtained different parts of gravitational wave spectrum and then merged into one, and that's how we got this picture. Unfortunately, I don't know. I would be very curious to know how these guys did the gravitational wave spectrum, and we could compare different methods. But that was the method which we described in our paper, and in my opinion, with this stuff, you can easily reproduce the gravitational wave spectrum and study its properties in more details. Also, we have been a bit limited to 2048 lattice. Maybe you have much better clusters like 4000 or even, I don't know, 9000, and then the quality will improve dramatically. Okay. Here I would like just to mention that, okay, as I said, one can always assume the proper time when the domain wall network is getting destroyed in such a way that you fit the.
We have 5 minutes left.
Oh, just 5 minutes left. Look. Yeah, but we started a bit later, no? Anish.
Okay, sure.
Huh?
Yeah, let's
Yeah. Just we started just 5 minutes. Could it be just 10 minutes? No?
Yeah, sure.
Okay, thank you very much. I will go quick. I will cut some not relevant part. Okay, so as I said, one can feed all this stuff to the nanograph data by choosing properly the destruction time of standard domain walls. There is just one problem. It's okay, it's not a problem. So as I said, nanograph considers domain walls as one of the favorable solutions, explanations for the stochastic gravitational wave background. But as I said, there is causality tail, which is n equals 3, the spectral index. While the best fit value of nanograph is 1.8. Okay, here the error bars are still quite large. Second, the domain wall spectrum is not just power law, it can be broken power law near the maximum. And then you can play with this to fit into the nanograph data. But maybe one could do slightly better. So at this point, let me talk about melting domain walls, which is, as I said, it's a scenario where the expectation value of domain walls is um, changing with time, changing with temperature. The expectation value is dropping inversely proportional to the scale factor. And actually, the picture is very similar in many aspects to the standard domain walls, but the tension is decreasing with temperature. And as a result, the energy density of domain walls, which is the tension times Hubble rate, is temperature to the power 4. And the domain wall problem is immediately eliminated in this picture. So the energy density of melting walls is decreasing relative to radiation. So as in the case, this suggests that the melting domain wall assumes that the melting domain wall network is in the scaling regime. And this can be proven. This can be proven. Basically, the picture is essentially the same. I will not stop more, but here the number of closed domain walls is much larger, which is quite interesting. And the ratio of closed walls to long wall is actually non-negligible at all. It's like about 30%, which is very big difference from the case of standard walls. And in that case, it sounds plausible that the standard mechanism of reaching the scalar regime works, like melting domain walls enter scaling by formation of closed walls which collapse into particles, just like in the case of closed strings. The gravitational waves from melting domain walls. The pictures here is very opposite to the case of standard walls. While in the case of standard walls, as I said, the largest signal comes from the later times. Here it's opposite because since the energy density of melting walls drops quite fast, the largest signal of gravitational waves is expected from the earliest possible times. And the spectrum is also very different. The spectrum, the gravitational wave spectrum is in the infrared, or okay, how to say, close to maximum infrared path. So this is the maximum which is due to the initial times of the gravitational wave emission. So only these initial times are relevant for the peak, and all the later emission does not affect the peak of gravitational waves. But the most interesting part is this slope, this infrared close to maximum slope, which is, so we estimated numerically 1.6 plus minus some correction. And this is exactly, okay, not exactly, this is very close, remarkably close to the nanograph best fit value 1.8. So, okay, of course, we should see how it goes with the future nanograph data, but we will be definitely interested to compare this with the future releases. So I'm looking forward. By the way, the fact that there is here 1.6, of course, it does not violate causality or anything. I've been speaking about the n equals 3 in the infrared. It's just here it starts in just much later at much smaller wave numbers. So there is here, if you will go into deep infrared, then you will also see k to the power 3. Okay, in fact, just let me mention that in our earliest work, we actually predicted n equals 2. There is a departure from n equals 2, a small tilt relative to n equals 2 towards 1.6, which is due to finite duration of the source. N equals 2 would be obtained if the duration of melting domain walls would be infinite, but with a finite duration, you get a small tilt. So the picture is actually quite close to what one has in inflation in this regard. Let me go into some, just mention some small obstacles. Not everything is so perfect, and in fact, we observed in some cases violation of scaling, but in quite particular regimes. So when the initial scalar fluctuation of the initial distribution of a scalar field prior to formation of a domain wall nectar is very large, in that case, if the initial scalar fluctuation is very large, then we have obtained the violation of the scaling. But we currently our line of thought is that it's just a systematics. And it's just due to the fact we formally observe a lot of closed domain walls, but we believe that it's just the estimator is becoming not very perfect, and it just misinterprets very small scale of fluctuations with closed domain walls. But this is some issue to be fixed. So, in the regime, when the scaling regime is getting violated, in fact, when the scaling regime is getting violated, of course, this impacts also the gravitational wave spectrum. But remarkably, the infrared part remains the same, and the spectral tilt remains the same, and the conclusions regarding nanograph are unchanged. So, due to the lack of time, I will not go into details, but what I wanted to say in the very end, just let me leave it as a message, is that the way I wrote the model for the melting domain wall, I just put there the expectation value depending on temperature. Of course, in practice, we would like to have some microscopic description, and it can be easily done by assuming that the domain wall field is actually coupled through some kind of portal to some thermal field living in the primordial bath. Okay, and in this way, one can construct this kind of high energy theory for the effective theory which we considered. And the only message which I would like to leave in order to explain the nanograph data, the field chi, the domain wall field chi, should be extremely weakly coupled. The weak couplings characteristic for it, well, they are not exceptional in physics. Axions also have extremely weakly coupled, weak couplings, but one should keep it in mind that this model is actually probably allowing to go into extremely weak couplings, maybe not acceptable by other experiments. Okay, that's essentially all. And let me skip the last part, which was about a dark matter. Yeah, in this model, if you will modify it, you will also get dark matter, but everyone can get dark matter, so it's not something potentially dramatic, maybe for some different talk. So let me just summarize. The main message is that with publicly available cosmolattice code, we can run simulations of domain walls, standard domain walls or melting domain walls, and with some rules summarized in our papers, one can hopefully reproduce the gravitational waves from domain walls. And yeah, and domain walls, especially melting domain walls, are promising candidates for explaining the gravitational wave background found by PTA, pulsar timing arrays. But one should not think that it's all limited to PTAs. There will be LISA, Einstein telescope, and so this investigation will be continued. So that's all I wanted to tell you. Thank you very much